Hey, hey everybody, welcome. Looks like in the chat right now we've got JDog2355, whoever you are, welcome. And Skinny Seahorse, I don't know who that is, it's kind of a weird name. But alright, so what I'm going to do first, I think, is I'm actually going to shut up for a second. I'm not going to say anything, and I'm going to put a problem up for you guys to do, to work on, just for a few seconds. And then we'll come back. So I'll give you guys about like 2 minutes. I'll also give some time for some other people to hop in if people are actually going to watch. We'll see. So you guys can do it. All right, here you go. All right. So let's kind of go through this one. I think this is the standard basic one, and there's a few little tricks to it that are helpful to know that we went over in class, and kind of see how it goes. If you guys have any questions, please use the chat. Type some stuff in, ask some questions. But let's get going. Oh, God. Oh, geez, the size. All right, there we go. So for this problem, we've kind of draw a picture for it. Now, something that would happen on an assessment, you'll always kind of have a picture given to you, and you're expected to draw your free body diagram for that situation, for that picture. So it'll probably look something like this. You've got a hand here. Try to draw my hand really quick. Oh, geez, it's not as good as last time. Oh, no. Yeah, that's all right. And then we've got our rope attached to, in this case, a rubber chicken. I'm going to draw that as a block because that's hard. All right, so we've got our hand, we've got our rubber chicken, and it's being swung in a circle. Now notice how it's drawn. It's drawn from this side view. So this horizontal circle, this thing is coming like at your face and then away from your face, and then at your face and then away from your face. And in this moment right here, it's perfectly perpendicular to you. So if we're to draw a free body diagram here, we've only got a couple forces that we can actually draw. So I'm going to draw my free body diagram right on top of the drawing. But as I do, if I'm going to draw it on the drawing, I'm going to make sure that I put a dot there, and I'm going to draw all of my forces coming from that dot. So when you guys go to do this, the first force you should always draw in any situation is the force of gravity. So we'll draw that guy in straight down. And then what else is touching our rubber chicken? It's clearly just the rope. That's it. That's all we've got. So if it's just the rope here, we've got our force of tension then, the only force a rope can go in the direction of that rope. So that's it. Now, as we said in class, we're ignoring the fact that in real life, this rope would be at a little angle. So notice this word right in here, perfectly horizontal circle. So that's kind of something that can't really happen in real life, but that we kind of assume for these kind of questions in physics. So we've done our first step, which is draw our free body diagram. The next step would be to kind of establish the knowns, what we know in this problem. Tilt this, okay, there, yeah, it's a little better. All right, so then we're going to establish our knowns, what we actually know in the problem, and go through. So we know in this case, we've got 1.25 meters. We've got this weird 6 complete rotations in 3 seconds, and 3 kilogram rubber chicken as well. So when we come to our knowns, we're going to say the mass of the rubber chicken here, that's going to be 3 kilograms, stated. That is a large rubber chicken. That's it's almost a 7-pound rubber chicken. I kind of want to watch that. I don't know about you. All right, so we've got the mass. Then we know the radius of the circle is 1.25 meters. Now this one, that's a little tricky. Let's take a look at the wording here. It says, if the length of rope between the person's hand and the chicken is 1.25 meters. So this length of the rope, from where their hand is to where the chicken is, if that's 1.25 meters, their hand is always going to be at the center of the circle. So in this situation, that actually is the radius. That's the distance from the outside, which is the chicken, to the center of the circle. Now, we don't know anything else, but the first question is, what is the speed of the chicken? So we can kind of figure out what the speed of this chicken is really quickly. We have an equation for finding speed. It's in our reference tables. We've used it a million times. It's, we'll do part 1 over here. V equals d over t. That is our equation for speed. Now, in order to do this problem, we have to think, all right, well, what's the distance this chicken's traveling if it's traveling in a circle? Well, since it's going around the outside of the circle, it's going to travel the distance along the outside of the circle, which is the circumference. So we can replace that with 2 pi r, the equation for circumference, right, over time. Now, we have to use a specific time. If we're talking about the chicken traveling 1 full circumference around, we have to take into account the time it takes the chicken to go 1 full circumference. So we're going to use capital T there, which is a fancy word called period, which is the time for 1 cycle. So to figure this out, we've got to go, all right, 2 times pi times the radius of 1.25 meters over the time for 1 cycle. Now let's look at what they gave us here. What we highlighted was 6 complete rotations in 3 seconds. So what is the time for 1 rotation? Well, what we can do is we can come to the calculator real quick, and what we want is we want to know the time per cycle. So what I'm going to do is I'm going to take my time value that I'm given. I've been given 3 seconds. Oh, let's turn the calculator on. There we go. All right, 3 seconds divided by the time for one of these. So the time for those 3 rotations was, or I'm sorry, no, the number of rotations was 6. We have 3 seconds here. Divided by 6 rotations. So when we hit enter and get our answer of 0.5, that is actually the time for 1 rotation. Right? So you're always going to do time divided by rotations if you're trying to figure out how long it takes for 1 rotation. Okay? So now let's kind of go back to the problem. Let's try and solve this thing and see what we get. Oh, we've got to go back to the calculator actually. Let's zoom back to that. Oh, I realize you guys couldn't see that at all. That's terrible. Okay. We'll work on this. It's getting better. It's a work in progress. So now we've got to actually figure this thing out. So we'll go 2 times pi, so we're going to go second pi, which is the caret button, times 1.25. So I'm just going to plug it in there, 1.25, hit enter. We've got our number divided by 0.5. So this thing is traveling at 15.7, so I'm just going to go to 3 digits. It's where we always like to round. It's always going to work out. 15.7 meters per second. So back to our normal solving screen, we can take that and bring that into our knowns. It's something that we know here. We know that the speed of this rubber chicken is 15.7 meters per second. That's going to help us out. Now we've got to know the tension in the rope. That's the next question. So for that, we need to come to our equations. Right? So we need to make equations in this situation. There's only one we can make. You have to ask yourself this question at the start of any circular motion problem. Is it moving in a circle? If yes, your equation starts with Fc equals. We need to know what the centripetal force is. Just like if an object's accelerating, we need to know what its net force is. Here, the object's moving in a circle, we need to know its centripetal force. So like Fc, centripetal force, is actually like the new F net. It's an F net that's specific to circles. So we're going to look at this, and we're going to come over here, and we're going to think about something. We're going to say, hey, any object that's moving in a circle, which way is it being pushed? And we've talked about this in class so much. It's one of the main focuses of circular motion. It's always being pushed towards the center of the circle. No matter what you think you would feel in real life, right? When we watch the people on the carousel, the metal bar of that carousel was pushing on their back. Therefore, that metal bar is pushing them towards the center of the circle the entire time. So if we want to know what Fc is, we just look and see which one of our forces, which is the force of tension here, is acting towards the center of the circle. And that's going to give us our answer. So now let's go down and let's solve part 2 here. So part 2 asks, in our problem, what is the tension in the rope? So I'm going to start with my equation that I invented. I'm going to start with this guy, this equation up here, Fc equals Ft. So scroll down, start with Ft equals Fc. So just like we did in previous units, you want to expand these equations. So you're going to go through, you say Ft equals, well, what's Fc equal to? It's equal to mac and cheese, which you guys can see on the screen right here. It's actually right there. Fc equals mac. Great. And then right below it is the next and important piece of this. This actually isn't an equation for forces, but it's important for forces, so we put it in here on your reference table. It's AC equals V squared over R. So I can replace this AC part here, this guy, with V squared over R. So when I go to write this in, I'm going to rewrite the entire equation. Ft equals m times, but I'm going to replace that AC with V squared over R. Now, as we've talked about in class, a lot of times it's very beneficial to write this as Ft equals mv squared over R. It's going to make our algebra a little bit easier. You can imagine that we get here by pretending this m is really m over 1, right? And we just multiply across the numerator and denominator. And I think this makes the algebra a little bit easier later on. So now all we've got to do is substitute in our knowns. We have an m, an r, and a v, so we're good. Mass 3 kilograms. So we've got a 3 kilogram mass being plugged in. Then we have the speed, 15.7 meters per second. Okay, and over the radius of 1.25 meters. Right? We're getting excited. We're getting towards the end of the problem. You guys are feeling great, aren't you? Right? And you're ready to plug it in. You're excited. You just wanted to get all that stuff in the equation, but stop! Stop! Just going to write it here. Watch. See where the cursor is? It's ready? Squared. Do not forget that squared. Do not forget it. You guys good? You sure? You sure? J-Dog, whoever you are you sure? All right, good. So let's go to the calculator screen here. Bring it up. There we go. And let's get ourselves an answer. I'll turn the calculator back on, clear everything out. And I'm going to do this in one step on my calculator. I'm going to open up parentheses, so we got 3, and we've got 15.7. I'm going to square that, divided by 1.25. That's all we need. That is all we need. We hit enter. 591.5.6. I don't know. Well, guess what? This is a great place to look at just the first 3 digits. First 3 digits are 591, but that 0.5 is going to round that up, so I'm going to say 592 newtons of force. So that's going to be the amount of force, the amount of tension in the rope for this die. So before we go on to the next question, do you guys have any questions in the chat right now? There's only 4 people watching. Actually, there's a bunch of people in the chat. I don't know, this thing doesn't update very well. It's not good. Yeah, it says there's only 4 viewers. So, anybody have any questions real quick in the chat room? Nope. Alright, well, you're going to have a second to ask them anyway. What I'm going to do is, just like we did last time, I'm going to bring it to another screen with this next problem we're trying to solve here. So we're going to zoom in on it, make it easier to read. Car going around a corner problem. And we're going to transition over and give you guys a few seconds to go through it. Ready, set, go. Alright, so let's go through this one. We got a car driving around a corner. Car's driving around on a asphalt track at 30 meters per second. What is the minimum radius of the circular track? So I'm going to draw a quick picture of what's going on here. Oh, my pen seems to be... Oh, no. Why is it doing this? No, pen, don't do this, man. Oh, no. That's not good. No. Computer, no. Oh, geez. All right, a little technical difficulty. Trying to save it real quick. Okay, let's see. Oh no, it's still on that. Oh no, it's. Well, this is awkward. I'm gonna put it back to the. Yeah, I don't know. I don't know why this is happening. This has happened before, and I can't really tell you why it's doing what it's doing. But apparently, it's trying to right-click everything that I do, which is not what we want it to do. This is awkward. So you know what I'm gonna do? I'm gonna end the stream. Come back in a few minutes and see if we can't get it fixed. Sorry, guys.